Hello. Hi. Welcome to Physics University. I'm Maggie, and you might have noticed the title of today is a little weird. I was laying in bed last night thinking about I ended up thinking about a Goofy movie. It's a fantastic film and I recommend it. It encapsulates just like 90s everything so well. Um but in the film uh in the film Goofy and his son Max are like sleeping in the car, and sleepy Goofy turns to Max and says, "How many cups of sugar does it take to get to the moon?" And Max responds, it's just a funny joke, but um being a physicist, oh, hi Fershay. Welcome. I'm going to be doing some calculations today. Also, thank you for saying hi. It reminded me that I should shout out John Hard BB22, who followed in between streams. So in a Goofy movie, how many cups of sugar does it take to get to the moon? Being a physicist, I am always thinking about little, uh, just like little calculations. Most physicists call them like back of the envelope calculations or napkin math. And it's just a way to, I don't know, do a quick calculation and figure things out. Thank you for complimenting my hair. I did it just for stream. Most of the days I don't do it at all. Yeah. Streams give me an excuse to like, I don't know, not wear pajamas, which is good. Um we all need to like dress up sometimes. I dress up for the grocery store and I dress up for stream. Um but anyway, I want to talk about just fun things you can do when you have enough like math background. There's an entire subreddit that does this called like they did r/they did the math. Um, but I want to investigate fun things that we can do. Um, Brendan brought up a lot of he brought up a lot of like Mario ideas, mostly because he was thinking about Mario. Like, how strong must the lasers creating Rainbow Road be to hold up the cars on the light rainbows? And all sorts of other stuff. So, without further ado, I'm gonna shrinkify myself and let us talk about how many cups of sugar it takes to get to the moon. So, there are a couple different ways we could do this. So let me get over here to my writing. How many cups of sugar does it take to get the moon? We could think about this in terms of like a tower of sugar. We do a tower of sugar. I mean, part of the joke is like, what does it mean? What does it mean to use sugar to get to the moon? We could do a pyramid of sugar, which I think is different. Pyramid of sugar. We could do what else do I want to do? We could just use the energy from sugar. We could do sugar as fuel. We could do sugar as fuel in a couple different ways. So we could do sugar as fuel as like for a rocket. Oh, thanks for the follow, Fershay. Um, and we could do like a bomb. Like you're shot out of a sugar cannon or something. I don't know. I don't know how that would work. But we'll figure it out. that's the point of today. So first, I don't know, we're gonna have to know some things about sugar and the moon. So let's make a box. I'll use orange because I feel like this will be important. Let's make a box of I'll move my stupid head out of the way. This is like the least interesting part. We need to know how big sugar is. So like a sugar, we want to know sugar size. What else would we need to know? We need to know the distance to moon. We need to know we need to know the energy of sugar for some of these. What else do we need to know? These will be good for now. Let's call like sugar size. Distance to the moon can just be D. And sugar energy can be, I don't know. We'll call it S sub E, sugar energy. And this can be S sub S, sugar size. So I don't know some of these off the top of my head. Thinking about like a grain, like a single granule of sugar, I'm thinking about just like white table sugar. A single grain of sugar would be a cube that's like half a millimeter. That's my guess. So we're say 0.5 millimeter. 0.5 millimeters. Let's look it up. Grain of sugar size. I was really dang close. So according to the Googles, grain size and sugar, measuring things. Okay. Let's look at Wikipedia, because I think Wikipedia is a good source. How are we going to keep the sugar together if we make a tower? Well, that's why I'm thinking about making a sugar tower, like the absolute minimum, like grains of sugar stacked on top of each other, which like physically is not a viable way to get to the moon. Not that any of these are viable ways to get to the moon, but that would be like the tiniest number of grains to get to the moon. But I'm also thinking about making a pyramid. And then that would take a lot more sugar. That would take a lot more. And like it's going to get blown away in the vacuum of space anyway. And like there are a lot of problems with this as a question, but that's what makes it kind of fun to explore, right? So, yeah, no, I don't know how we're going to keep our little sugar grains together. Super gluing sugar grains together or something. Assuming that the sugar sticks to other sugar grains. We'll go with that. This is just making me want candy. Okay. Sugar. There was a section on grain size. Types of sugar. Sugar and things. Refining sugar. Crystal size. Okay. Coarse grain sugar, known as sanding sugar, 1 to 3 millimeters. Okay. Granulated sugar is about, 0.6 millimeter crystals, known as table sugar. Okay, so we'll go, castor sugar is really fine. It's 0.35 millimeters. We could create a syrup tower, if we like stuck the sugar together with water. Could make a giant rock candy mountain. That's a fun song. If you've never heard it, Big Rock Candy Mountain's like this old cowboy song. It's great. I love rock candy. Okay, so let's go for the sake of calculation. So this is something, problem solving thing whenever you do estimations. Physicists are not very, how shall we put this, precise. When we do back of the envelope calculations, we want to be quick and marginally accurate, but like kind of getting the calculation out there within an order of magnitude is more important than like being super duper 10 significant figures accurate. This, in my opinion, is one of the big differences between physicists and engineers, is that engineers will take the time and go through and find like decimal precision on things, and I can't do that. Physicists won't do that. So we could go with coarse grain sugar with 1 millimeter grains. We could go 1 millimeter grain, or we could do granulated sugar 0.6. I'm gonna go with my 0.5. That seems half a millimeter. You know what? No, let's just do 1 because that's easier. Like I said, the difference between a half and a 1 is not going to be that big of a deal. So let's go back to here. We're going to say that rock candy's good. It tastes, I mean, it's just like sugar, and sometimes the manufacturers will like just dip it in like artificial flavor, like fruit flavoring usually, but like it's just a stick. It's just a stick of rock crystals. You can make it yourself by dissolving like we're gonna go half to 1 millimeter. And this is a cube. I once went to a really fancy like hot chocolate with the president of the university thing, which was a load of BS that actually me and some of my friends brought protest signs to, because we had students on campus who were like starving, like literally were food insecure, and the president was holding this like fancy hot chocolate winter event, but they had, I remember very distinctly that I ate the food, took the hot chocolate, like our tuition dollars were paying for it, but they had little tiny rock candies that you could use as stir sticks for your hot chocolate, and it would like dissolve the sugar as you stirred. It was very bougie. So I took a lot of rock candies and just shoved them in my pocket and just left. Okay, so we've got sugar size. We're doing half to 1 millimeter, and then what else do we need to know? Moon. No, that's the wrong page. Moon. Where is the moon? Okay, we're gonna guess. Distance to the moon. I'm gonna say that it is, no, miles, gross. Gross. Don't want miles. The moon is so pretty. Freaking love the moon. Okay, moon is how many? Perigee and apogee, which are the farthest and closest that it is to the Earth. We'll say, for the sake of argument, so this has perigee and apogee, which I think are, yeah, those are the distances from the Earth. Because the moon, like most celestial bodies, does not actually orbit in a circular orbit. It orbits in an ellipse. So perigee is the closest, right? Apsis. Yeah. Yeah. Near 2 extreme points. Okay. So the moon is between 360 and 400 kilometers away. So let's just say 400,000 kilometers. I think that is fair. Like I said, I like estimating. 400,000 kilometers. I can't do. Okay. 400,000 kilometers to the moon. Okay, so right off, if we wanted to make our tower of sugar, we would take, it would be like the size of a grain of sugar, like the height of one sugar. And we want to divide the distance to the moon in steps of sugar. So distance to the moon divided by things of sugar, that's going to be 400,000 kilometers. Oh boy. 400,000 kilometers divided by, yeah, we're not using the 0.5 millimeter. We're going to use chunky little sugars. Divided by 1 millimeter pieces. And a good thing that I always emphasize to my students is checking units. So number of grains of sugar should be how far away is the moon divided by how far of a step can 1 grain of sugar take. And I have units of length divided by length. So I should get something unitless. And a number, just an amount, is a unitless quantity. So grains of sugar should be a unitless quantity. So this is really 400,000 times 10 to the third meters over 1 times 10 to the negative 3 meters. What a sweet calculation. Thank you. That is very cheeky, but I like it. So then this would be, oh, this is grody. 400,000 times 10 to the 6th grains of sugar, which 400 times 10 to the 9th. So this is 400 billion grains of sugar to get to the moon. Just stacked on top of each other. I don't like this. Not because, like, the number doesn't make sense. It's large. I expected it to be big. A grain of sugar is very tiny. If we were using not coarse grain sugar and we were using table sugar, it would be twice as big because there was a factor of 2 in how big those grains were. But this is not, like, this number is just huge and I can't comprehend it. So I want to get this into a format that I can make sense of. So this is grains of sugar. I want to figure out, I mean, the prompt was how many cups. So I need to figure out how many grains there are per cup of sugar. And of course, a cup is an awful, horrible non-metric unit. So a cup, 1 cup is equal to, it's like 235 mils? We can look this up. These are things, this is another thing I always tell my students. It's like, don't waste your brain memorizing almost anything. If you can avoid memorizing, do it. Don't waste brain space on this. So we wanted to know Cup to mill. Cup to mill. Haha! I was right. Oh, you can't see it because my big old head's in the way. So one cup is this many milliliters, and I know that 1 milliliter, a milliliter is equal to 1 cubic centimeter. Right? Yeah.
Milliliter and cubic centimeter.
cc to mill. Yeah, I was right. So a cubic centimeter, something that measures a centimeter cubically. I'm eloquent. Is 1 milliliter. So there are, was it 35? It was 37. It was 37. This is wrong. So that many milliliters, so 237 cubic centimeters is 1 cup. And we know that this might not actually be that many cups of sugar. One grain of sugar is equal to 1 millimeter cubed. Because we were saying that 1 grain of sugar is, oh boy, art skills. That was like the worst way to draw a cube. I'm super embarrassed. Okay, let's let's draw our cube better. Okay. We got a cube. That's a better cube. So each one of these sides is going to be 1 millimeter. And so the volume of our sugar is 1 millimeter cubed. So now how many little sugars do I have to stack together to get 1 centimeter cubed? Well, there are 10 millimeters in a centimeter. So that means I'm going about this a very weird way. Like, I could do this conversion differently, but I like thinking about it as I'd need 10 grains by 10 by 10, right? To get a cube. Volume to volume. So I'd have to line up 10 grains to get a centimeter, and I'd have to do that in each direction. So 10 times 10 times 10 is going to give me 1,000. Oh. Yeah. Okay. So this is... Yeah. Anyway. So there are 1,000 grains per 1,000 grains of sugar per cubic centimeter of sugar, which means that there are 237 cubic centimeters times 1,000 grains is 200,000 grains per cup of sugar. Okay. So then go back up here. Oh yeah. So now I have 400 times 10 to the 9th grains divided by 237 times 10 to the 3 grains per cup. And this should, with units, give me a measurement of cups. Um, the physicist in me is like saying just make this 200 because it's easier. And I don't want to get a calculator, so that's what we're gonna do. So we're gonna get 2 zeros cancel. 2 times 10 to the 6th cups. 2 million cups of sugar. 2 million cups of sugar. Okay, so I'm gonna go back up here. A tower of sugar, we would need 2 times 10 to the 6th cups. Sweet. Sweet. It's sugar. How heavy is a cup of sugar?
Can't be more.
Well, I think sugar. Let's look up the density.
Gotta be like.
Ooh. Grain sugar. How heavy is sugar? Density of sugar. Give me.
I mean, it's gotta be less than 8 ounces because that's water and it's less dense than water.
Crystals. Health effects. Sugar. Oh, this is also going to be very useful. Granulated sugar.
This is a baking thing. The conversion's just gonna already 7 ounces.
7 ounces. A cup of sugar is a half a pound. Ooh, that makes me feel really gross thinking about how much sugar I eat when I bake. Okay.
How much did you find? How many cups did you get?
We need 2 million. 2 million cups of sugar, which is 1 million pounds. So we need 1 million pounds of sugar to get to the moon with individual single grains stacked on top of each other. So, this 1 million pounds. Yes, sugar is a terrible form of space travel, and this is the lower bound, y'all. This is the lower bound on because this is a single grain tower held together by eldritch magic. This doesn't seem very efficient, and a pyramid of sugar is going to be even worse because a pyramid of sugar. So I'm going to switch to another color for pyramid. A pyramid of sugar would be not a pyramid; it'd be more of a cone.
Yeah, for the pile.
So like, here we go. Here's our. This is distance d up to the moon, and the volume of a cone is 1/3 pi r cubed. Yes. Times the height. Oop.
1/3 pi r squared h.
Is it 1/3 pi r squared h?
Well, that's great units.
Well, okay, just because it has the right units doesn't mean that it's correct. I know it's
Disagree.
I know it's 1/3. There's a factor of third. Pi r squared h. Alright, so that's the volume of a cone. A cone. So I know how tall my cone has to be. And in the limit that the radius of our cone goes to 0, we just get the tower again. How big of a base do you think we need for our cone of sugar? Like, how do we limit this? How do we limit this cone? Like, I mean, the most structurally stable cone would be one where this angle is 90 degrees, right? I mean, I could have a really What is the most structurally stable cone? Is it a 45-degree cone? I mean, if I'm looking at the profile of my cone, I've got some sort of isosceles triangle here, where this angle and this angle are the same. But what? Do I need to look up like granular materials? Like, how do granular materials?
Angle of repose is loosely approximated by the tangent of the angle equals the coefficient of static friction of the material.
Sorry, I just got dumped some information. Okay, so the angle.
It's called the angle of repose.
This angle.
Theta.
This angle theta.
Tan theta is approximately mu s. Tan theta. Okay, fine. Mu s.
What is S?
No, sorry. Like mu sub s. Static friction.
Oh.
Like it's real simple.
Oh. Okay, so we need to know what the static friction of sugar on sugar is. Okay. I'm going to approximate that.
Super cool.
That this is a very cool equation. Oh, and again, my big old fat head is in the way. I should just make myself tiny. Pew. There we go. So we need to know what the coefficient of friction is for sugar on sugar, which I don't think I'm sure someone has figured it out, but I'm not going to imagine that this is something that's like documented and easy to find, and it's not a calculation or it's not an experiment that I'm going to conduct myself. I would guess that sugar, being a crystalline grain substance, is going to have this approximately the same coefficient of friction as like sand of the same size. And sand is something that probably has a lot of information about its coefficient of friction. So sand on sand of grains that are about 1 millimeter in size. I don't know. Let's figure it out. Sugar. Coefficient of friction sand. I'm not even going to look up sugar because it's not going to be
hard to do.
It's not even going to be useful. Friction coefficients between. What is this? This is civil engineering from the Navy report. Oh my goodness. I love finding weird stuff like this. Coefficient of friction between calcareous sands and some building materials and their significance. What is this? Calcareous sediments have proved troublesome for engineers. Ooh, oh, oliths? Okay, no, that's not what that's really cool. Sliding, I don't want sliding friction. Cohesion for soils. Oh, cool. Boo. Table of friction factors for I don't want dissimilar materials. Clean to medium sand. Okay. I mean, I'm guessing the coefficient of friction is gonna be like 0.5.
So
0.4.
I saw something measured earlier called the internal friction angle.
Internal friction angle? What's that?
And I don't know what internal friction angle, but I've seen it referenced.
Sand. Soil friction coefficient table. Let's look at that. Concrete on soil. These are very important things if you were going to be some sort of a structural engineer. Find a coarse sand, very coarse sand. I don't know what this table means. Dude, soil science is weird. Uh-huh.
Internal, they're all between 30 and 45.
Yeah.
Like, call it 30 something. Just
okay.
Run with it.
So we'll say this this one's giving me the actual angle. So like dry sand. Let's say dry sand about 30. We'll say 40. 40 degrees. 35 degrees. Let's say that our angle is approximately 35 degrees.
Okay. Rice is 25 to 30. Powdered sugar is greater than 40. You figure granulated sugar is somewhere in between those two.
Granulated sugar is going to be in between rice and powdered sugar as a granular material. So yeah, we'll go 35 degrees. That means on our cone, I've got 35 degrees here, and I know the height has to be a distance d. I got to use my trigonometric knowledge to figure out the radius. R, this is 35, this is 90, this is d, which means that this is going to be the square root of d squared plus r squared. You know, I'm going to keep doing it, but like I think the single grain tower is cooler than a pyramid. Moving on. 35, so this is going to be 65 degrees. So sine of 35 over d has to equal sine of 65 over r. This is the law of cosines. No, law of sines. Law of cosines is worse. So then we get that r is equal to d sine 65 divided by sine 35. No, I have to get a calculator.
Call it root 2.
Oh.
It's about a 30, 60, 90 triangle.
Oh, this is about a 30, 60, 90 triangle. See, again, physicists. We're just going to say this is this. Wait, no, it would have been 55. I know how to add. We're yeah. Let's just do 36, 90. Okay. So r is going to equal root 2. No, it would be d over root 2. So that's the shorter side, right? D. Root 2 times r would equal d. Am I bananas?
The bigger side.
D is the bigger side, so root 2r would be d.
Yeah.
Because root 2 is like 1, it's just less than 1.5. Okay. Oh, okay, so already a problem is that if this has to be, if d, yeah, yep. So r equals d divided by root 2.
By the 30.
The long?
Because the 30, 60, 90 that you set up, the 60 is the true angle in the corner, and the 30 is the half angle. So r should be longer than d. So sorry, what I'm saying is 30 degrees, right, means the bottom side is longer than the top side.
Ah, the bottom side, yes.
You have a 30, 60, 90, but you
I have it backwards. I have it
where you want it
backwards.
to be.
I have it backwards. Okay.
It's okay.
So r is equal to root 2d. Because this side, being across from the bigger angle, is going to be longer. And this side, being across from the smaller angle, is going to be smaller by a factor of root 2. All right. This might be more problematic than the single tower, because this is telling me that the base of my pyramid has to be bigger than the distance to the moon. This is telling me that how far away is the moon? 400,000 kilometers. Okay, so the radius, not even the full base, the radius is going to be 1.4 times 400,000 kilometers. This sugar tower is not going to fit. The sugar tower is not going to fit on the surface of the earth, like at all. Yeah, no, the earth would be just like totally coated in sugar. So I don't think that this is a viable solution. So I'm going to make note of that. Earth, too tiny. This isn't even getting into having that amount of sugar. Yeah. We should take our single grain tower and calculate it in terms of annual consumption in the US. How many days of sugar consumption would get us to the moon?
How many grains was the tower?
The grain? How many grains?
Yeah.
400 billion. No, 400 billion.
400 billion.
400 billion grains. Yeah. Okay. That's about... I think that's on the order of how many trees there are on the Earth. It's definitely on the order of how many stars there are in the galaxy. So this isn't a good idea. Let's do sugar. Let's do sugar as as fuel. Let's do sugar as fuel. So let's pick out a new color. Do green. Okay. So that was a whole load of not a good path to go down. Like we'd have the earth here. And this would be our pyramid of sugar.
The pyramid of sugar requires about 1/1000th the grains of sand on the earth.
In one place, though.
And yeah, constructed into a single man. There's some entropy problem.
We are being punished for our hubris. Let's keep going. Here's my sugar tower. Here's the moon. Fun fact, the distance from the Earth to the moon is approximately 30 Earths. So 30 Earths can fit between the Earth and the moon. And the Earth itself is 4 moons across. So the radius of the diameter of the Earth is the same as the diameter of 4 moons, which I think is pretty cool as like a scaling argument. So like we're 4 times bigger than the moon, but we're 30 Earths away. All right, so we got our little Earth wearing its giant dunce hat of sugar. Let's do sugar as a fuel. So as a fuel, Sugar, we're going to look up its caloric density. Sugar calories. Okay, so I'm just going to go back to that page I had open of sugar. Granulated sugar. Per 100 grams. Per 100 grams, which is roughly a half of a cup. Because that's 3 ounces. And we said 7 ounces was a cup. Okay, so per half cup of sugar, we have 1,600 kilojoules. Hold on. Sorry, let me make this big. I'm just giggling for a second. So right here. This is our table for sugar. What's the other 0.02%? What part of sugar isn't calcium? There's calcium in table sugar? Okay, apparently there are trace amounts of calcium and potassium in table sugar, enough to make it not 100% sugar. But it's basically 100% sugar. So we've got 16. We have 1,600 kilojoules per 100 grams, and 100 grams of sugar is about a half cup, we decided. Are there more grains of sugar in my diet or in this problem? Ask Magic 8 Ball. Magic 8 Ball says, if the Twitch gods grant it. Which means that we would have about 3,000. How many? Wait. 100 grams is 3.5 ounces. So that means that 200 grams, that is not a 2. That is not, okay. We're going to back this up a little bit. 200 grams is equal to 7 ounces, which means a cup is about 8 ounces of sugar. It's a half pound. So let's say 35. So I'm going to say about 237 is about 8 ounces, which means that 1 cup of sugar. That's wild that sugar almost has the exact same density as water. But I guess it makes sense. Does it? I mean, it would make sense that, because that means that the density of a water sugar solution is the same as water, which would be beneficial because a water sugar solution is what fruits are made out of and bodies and stuff. So it makes sense that it would be on par with water. Does it? I don't know.
For incredibly trace amounts of calcium, potassium, and fluoride and
selenium. Yeah. So, this would be 3,200 kilojoules. So we'll say that another third of that is 33. A third of this is 4. We'll say that a cup of sugar has about 35. No, it needs to be more than that. 36. We'll do 3,600 kilojoules. All right, 3,600 kilojoules in a cup of sugar. Now we need to figure out how many joules of energy it would take to get to the moon. All right. So the sugar calories, we're saying that it has 3,600 kilojoules per cup. Rough estimate. Now we need to figure out how many kilojoules it will take to get to the moon. So, really all we need to do is achieve escape velocity, right? We need to get out of the gravitational pull of Earth, and as long as we're headed towards the moon, we'll keep headed towards the moon and we'll crash into the moon.
Bye. What escape velocity?
We will die if we go at escape velocity when we hit the moon. Well, we're also... I don't care. I don't care if we die. I mean, there's not... That's just the easiest way to do this. Unless I'm, like, forgetting something.
Minus GMM for our Earth surface. 30 times that. I feel like that's probably going to be like half escape velocity or something, so you're on the same.
So...
You might as well just do escape velocity. It's going to be about the same.
Well, okay, if we do... Because, like, I'm looking at the gravitational potential, the difference in potential, right? We're looking for a difference in gravitational potential between the Earth and the moon from oh, we could make this complicated.
Yeah, like from Earth surface to moon surface.
We could look at from Earth surface to moon surface and include the moon in our calculations. So as we get closer to the moon, we'll have more gravitational pull towards the moon. But that...
It's so tiny.
No, it's not that tiny. It's like a sixth of Earth's grav.
Right here? Or on the moon surface?
On the moon surface. Okay, we'll call it negligible. The moon is a tiny guy.
Yeah, but how much closer to the center of mass of the moon are you on the moon surface than on Earth's surface? It's not a factor of a sixth in proportion.
It's a factor of 4.
What I'm saying is the effect is going to be a factor of like 1,000.
Sure.
On your energy.
So, our initial... Well, yeah, let's do it as an energy calculation because I don't want to do velocity garbage. So my potential on Earth we have a energy of G M me over the potential is GMM over R, and the R squared is gravitational force. Okay, so we've got potential energy this on where this is 1 Earth radius. When we get to the moon, the gravitational potential energy from the Earth, this is mass of the Earth, this is mass of me as a little person, is going to be 30 times farther away, 30 radiuses of the Earth. Hey, that knowledge about how far away the Earth is from the moon in Earth's is very relevant here. Okay, so really what we're saying is my potential energy is changing by a factor of 29/30ths. So, my change in potential energy is going to be 29/30ths of a GMM over R. Yeah. Because I got 30/30ths minus negative. Wait, final minus initial.
Gain energy as you go out.
I gain energy as I go out.
So.
Yeah.
Or from a negative number.
Yeah. So we have to put 29/30ths of GMM over R stuff to get. That's the change in our potential energy as a because of the difference in distance from the center of the Earth. Okay, that's fine. I want to know what that is. What is a GMM over R? So I know GM over R squared is 9.8.
That's exactly what I was.
Okay, I'm gonna do some shenanigans. Okay, so GM over R squared. This is you might have seen a like gravitational acceleration near the surface of the Earth. That's this. This is 9.8. And when I multiply it by a mass, I get the force of gravity on me at the surface of the Earth. Okay, so this, yeah, we're getting into real physicist hours right now. Okay, 29/30ths, which I might just call 30/30ths. Let's be real here. Is 10 meters per second squared times my mass times, if I squared this here, I got an add an R up here, times the radius of the Earth. Okay. Okay. And this will be joules. Yeah, this will be joules. Okay. So now we got to deal with a couple things. Let's look at what is the radius of the Earth. Radius of the Earth. Moon. Okay. Moon. A moon. Let's click on to Earth. Hello, Earth. Radius. Mean radius. Okay. 6,000 kilometers. We're going to estimate 6,000 kilometers. So R equals 6,000 kilometers. All right. If it's 6,000 kilometers away, sorry, from the center of the Earth, what are we trying to move? What are we trying, like, what are we trying to get to the moon? I gotta know what it is I'm trying to get to the moon to be able to do this calculation. I could figure out, like, the change in potential, fine. Just me. I'm gonna go to the moon. Okay. So, I don't want it to be a whole spaceship, because that's hard. Let's just shoot me out of a cannon. We're just gonna shoot me out of a cannon. How much energy do I need? So, let's say me in all my space gear, for the ease of calculation, let's say that me and all my space gear is 100 kilograms. Me and my space gear is 100 kilograms, so we've got 29/30 times 10 meters per second squared times 100 kilograms. Yeah, because we get a Newton meter. This is a Newton times 6,000 times 10 to the 3 meters. That's a joule, y'all. We did it. So that's gonna be, hi, Juno. I have a cat. She's coming to say hello. So this is, we're gonna do some quick maths here. All right. So this should give me 29 times 6 divided by 3. Hi, friend. Cat break. Come here.
29/30 is 58/60. You just turn that 6,000 into a 5,800 and call it done.
That's what I was gonna do. Say hello, lady. Here. Cat break. Cat break. Be cute. Oh, she is unamused right now. Hi, baby. Okay, do you want, show off your cute tummy. Very good. Very good. Okay, you can go now. Are you, nope, you're just gonna get hair all over me and rub on the microphone. Thanks, cat. I love you too. I love you and your hairy butt. She is quite big. She is very large. And she thinks that it's dinner time, but it's not dinner time for another 2 hours, huh? Oh, bonk the microphone. Come here, babes. Juno is named after the Juno satellite that went to Jupiter to take pictures. And she just chillin'. Hi, can I finish my calculation? Okay. You can huff and puff all you want. Oh, she's mad because you put your papers in her bed. There you go. She has, I'll show you, she's got a little bed there. And Brendan's papers from teaching were all up in there. Let's make my head smaller again. Okay. Okay, so 29/30. We're just gonna make this a, what did you say? Turn this into 58/60 times 6, which is gonna be 58/10. All right. So we have 58/10 times 10 times 100 times. If any of my students turned in work that looked like this, I would give them the worst grade ever. I would give them the worstest grade ever. Brendan, throw in a math time for inspiration. Oh, you did it wrong. You did it right. Yes, you did it right. Okay, cool. I can't see the BTTV emotes on my end. Oh, no, don't gunch me. Don't gunch me. I'm doing the calculation. It's fine. So now this is now 1,000. 1, 2, 3. 3 more. All right, so we have 58. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, hey, wow. Look at this. It's going to be our friend 10 to the 9 again. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So we have 5.8 times 10 to the 9 joules. Okay. So this is the change in potential energy from the Earth to the moon. The change in gravitational potential energy that I would experience. So I need to put in that much work to get from the Earth to the moon. So this is delta U grav. This is an important number. So now we want to figure out how many cups of sugar will equal that. So one thing we should think about, though, is I'm covered in cat hair now. What sort of efficiency do we think our sugar cannon can provide? Is the sugar going to, like, perfectly, we're able to get all of the energy out of every grain of sugar? How much are we going to lose to heat? How much are we going to lose to sound? What is our energy conversion? And so, for reference, I know that like gasoline engines run 40% efficient at the best of times. So we'll do like the most efficient. You were either efficient or not, so 50% efficient. Wow. That's there's two options. You're either efficient or you're not, so you're 50% efficient. I dropped my pen. Come back here, pen. All right. That's an opinion there. So, let's calculate the absolute minimum. Like 100% efficiency, best case scenario, every grain of sugar is given all of its sugary goodness to getting me to the moon, which is not true. Yeah, I've been calculating how many cups of sugar to get to the moon for the past hour. But I've done it a couple different ways. So the first calculation that I did was a single tower of sugar, like a single grain, all the way to the moon. How many grains would you need? And then I tried to calculate, like, that's not very realistic. Let's do a pyramid instead. Like just a pile of sugar. And that was also not very realistic. So we're going to do an explosion now. And instead of using the physical properties of sugar to physically ladder us to the moon, we're going to use the chemical properties of sugar to explode us to the moon. And it'll be great. It'll be great. So this is roughly the potential energy. This is the amount of work I need to do to get to the moon. Very rough estimate. And back up here, we had calculated that there are approximately 1,600 kilojoules per cup of sugar. So, assuming 100% efficiency in my sugar cannon, because let's be real, this is not going to be a rocket. We're just going to, like, yeet me to the moon. 3,600 kilojoules per cup of sugar. So I need to take 56 times 10 to the 9 joules to get to the moon, divided by 3.6 times 10 to the 6 joules per cup, is going to give me, my estimation brain is like tingling right now, and it's saying, just say it's 6 divided by 3. I'm almost to the end, and then we can talk about whatever you want to talk about. Okay, 10 to the third. 5.6 divided by 36. Oh, okay. Well, I'm just going to say that 56 is, what is it? 36 plus 20 is 56, which is like 1.5. Yeah? Yeah? Are we on board with that? I think we're on board with that.
It's very nearly 1.5.
It's 1.5. 1.5 times 10 to the 3 cups. So assuming perfect efficiency, we only need 1,000 cups of sugar to get to the moon. That feels very small. Again, this is 100% efficiency. So let's go back up. So this was 1.5 times 10 to the 3 cups at 100% efficiency. So on the scale, like on the reasonableness scale, it is better you use less sugar by several orders of magnitude to burn as fuel to get you to the moon than making a tower of sugar with the least amount of grains possible. The pyramid I had to abandon because the base of the pyramid you would need to get to the moon is bigger than the Earth by quite a bit. So, yeah, no, the sugar tower, the single grain tower of sugar all the way to the moon is a lot. So, I think what we've learned from talking about sugar to the moon for an hour is that different types of materials have different advantageous properties about them. Sugar's advantageous property is its like energy density in like a chemical energy density and is not its physical size. So it would probably, like, if I had steel, making a steel tower to the moon would probably be better than trying to combust steel and shoot me to the moon. Don't even know how combusting steel works because it's not made out of carbon. There's some carbon in it. There's carbon steel. But it's still not going to be... Yeah. So we use sugar for its, not for its structural properties. And again, now I just want, like, rock candy. But explosions are very efficient. Like, you do lose a lot of, like, heat and sound and stuff, but compared to, like, I mean, like, what? You just throw stuff. Just eat it. I'm a little sugared out. I have, like, other cheeky questions we could ask. Brendan was wondering how... Oh, yeah. What was your question? Because I can be cheeky all day. But I will take a break from being cheeky to answer a even semi-serious question. I need my candy. Oh, bosons and fermions. Heck yeah, we can talk about bosons and fermions. Okay, so bosons and fermions. So very broadly, particles are broken into two very large categories, called bosons and fermions. And I'm going to say something that is very not useful, but it is. We'll get to how it's useful in a second. So bosons are the types of particles that obey Bose-Einstein statistics. So these obey Bose-Einstein statistics. By particles, we mean excitations. Sure. Yeah. I don't know. I'm gonna, particularly when talking about bosons and fermions, like, by calling them bosons and fermions, we are specifically talking about, like, the particle model. And so, yes, as something, they can be, both sides are excitations in some underlying field. Yep. So, like, the Higgs boson is a particle that obeys Bose-Einstein statistics, and it behaves like all other bosons do. And it is also, if we look at it from a quantum field theory perspective, an excitation in the Higgs field, where a fermion is a particle that obeys Fermi-Dirac statistics. And it obeys Fermi-Dirac statistics, and then can be talked about as a particle, as a fermion, or more broadly as a bosons and fermions are not living in different fields. I mean, they're living in different fields in the same way that, like, an electron is a different particle from a quark or a proton. A photon is a particle and an electron is a particle, but they're different particles. I think a good way to think about so in the standard model, I'm actually going to just look up some standard model stuff because it'll be we'll look at the Wikipedia page. We'll look at CERN's page. We're also going to look at these. Particle Zoo. This is one of my favorite things because I like crafting stuff. I like making, I crochet a lot. And there was an artist who decided to make these particles. So this is the Particle Zoo. And they have, every single particle, and they're even, weighted differently depending on the masses of the particles. It's super adorable. It's stinking cute. They're expensive as all get out, though. But, you could buy yourself a little Higgs boson, and its tag tells you all about the Higgs, when it was discovered, how heavy it is. Higgs bosons is chonky boys. Anyway, so in the standard model, we can look at, I want to look at the bottom quark. I want to look at the charm quark. Just give me, I do not understand. This was something I didn't understand when I was at CERN either. Their choice of, Their graphic design isn't bad, but it is weird. Like, they make some interesting choices. Okay. So, in the standard model, we have, got it. I understand. There's cookies. They exist. Okay. So, I don't like that picture either. Dang it. Give me, oh, this is beautiful. Okay. We're going to look at this. In the standard model is used to describe fundamental particles. And so we're just going to look up standard model again. Standard model. So in the standard model, we have, thank God, just, oh my God, just give me the picture. Okay, this is all I want. So particle physics is built up on this idea that if you have, I mean, this goes back to like the Greek idea of an atom. So the Greek idea of an atom came from the word atomos, meaning to like be a building block. It is the smallest component. Because Greek philosophers were like, well, if I have something and I cut it in half, I have two of that thing. And then if I cut that in half, and you get this like reverse Zeno's paradox of getting smaller and smaller and smaller and smaller. And so at what point can you not split it anymore? At what point do you reach like the fundamental building block of that reality? And so an element, like on the periodic table of elements, we call them atoms because they are one of the smallest building blocks that we have. Then you get to, well, can you split an atom? Can an atom be made smaller? And it can. It's made out of protons and neutrons. And so we continue to look further in and further in and further in, and we just zoom. Oh, that's a really cool graphic. I'm actually I'll have Brendan find it for me and we can look at it later. But as we zoom in and in and in, there comes a point where you can't zoom in anymore, where the particle that you're looking at does not have any more constituent pieces. So, for example, with like a hydrogen atom is made out of electrons, protons, and neutrons. Now, the electron, we've tried colliding them at colliders and tried smashing them apart and tried ripping them apart, and you can't do it. An electron is a fundamental particle. An electron is not made up of anything else but an electron. It is inherently just fundamental. The proton, on the other hand, we were able to pull that apart. You were able to tease apart a proton using giganto stuff. What does it mean for an excitation to be divisible? So yeah, so there is any sort of interaction I do with an electron, there has not been discovered, and there is no mathematics to support that there is a electron, there's something that makes up the electron. So with the idea of field theory, the idea of, no. You are not going to go up there. Get down, fatty. Sorry, I have a naughty cat. Fundamental quantum field theory, it says that there is like a field for each fundamental particle. And so bosons and fermions are classes of particles, and bosons and fermions are classes of particles that behave similarly to each other, particularly in this statistical sense, where a But like there is an electron field in the universe, and excitations in that broad field that covers all of space, an excitation in that field will produce an electron. So there are lots of excitations in the electron field, producing lots of electron particles. And when those fields interact with each other, so when you have like quarks in the quark field interacting with gluons and other quarks, that becomes a proton. But there's not like a proton field. So that's what I would say about for an excitation to be like indivisible, is that it is made up of one field. One field constitutes this particle. Whereas a proton is constituted of quarks and gluons. But there is nothing but a gluon in a gluon, which kind of feels like circular and redundant. Do different fields corresponding... Okay, so your question is, do different fields corresponding to different particles just overlay each other without interactions between them? So this is getting exactly to what it means to be a boson or a fermion. So certain fields will interact with certain particles, and certain fields will interact with each other, other fields will not interact with each other. And that's what... that goes kind of back into this idea of unified field theory, where we want to go back to where like everything was one single field. So for example, right here, photons, actually we're gonna go to this one. No. So the difference between fermions and bosons in a statistical sense is which type of statistics they obey. But in a like conceptual sense, fermions are like matter, or fermions are matter. They make up atoms. So everything over here that's a fermion, it makes up matter. Where everything that's a boson, everything that makes up a boson or is a boson is a force carrier. So electrons are fermions, but a photon is a boson. A photon is the particle version of the electromagnetic force, the electromagnetic field. And so particle physics, like the particle model of particle physics, is basically saying if I have two electrons and they want to interact with each other, the two electrons will not interact with each other. They do not talk to each other. The two excitations in the the electron field, don't know that the other one exists necessarily. But they can interact with each other by like talking to each other through a carrier particle. So one electron will spit out a photon, and the photon goes, and then the other electron will eat it up. And that is how any sort of interactions happen, is through bosons. So in a proton, for example, a proton is made up of 3 quarks held together by gluons. What does it mean to be held together by gluons? It means I've got 3 quarks that are next to each other, and they are rapidly exchanging. Sometimes they're called exchange particles, or force carrier particles, but they're exchanging these force particles. They're exchanging gluons between each other. And that's what keeps them together, is that they have like this back and forth conversation with each other. But the quarks themselves like don't overlap. They don't interact with each other. Yes. We're decomposing field theory into elementary fields corresponding to it, like irreducible particles. Yep. Yeah. So fermions could be considered like repositories for bosons in a way. One of the big... I do want to talk about the statistics part, because that is how we decided to classify them, because of how they behaved. And then I'm not sure about the history, but I think we discovered all these different particles, and we saw that hey, electrons and muons and tau particles all kind of behave the same, and they follow Fermi-Dirac statistics, but photons behave differently. And then later it was noticed that all of the ones that follow boson statistics are all force carriers, and all of the ones that follow Fermi statistics are matter particles. Yeah. Fermions don't really do anything, but spit out and receive bosons. Basically. You can have... Right, and so the different particles basically are only allowed to... It's almost like a game of Hungry Hungry Hippos, where each particle will eat and spit out different things, and eating something and spitting out something can change what you are. For example, an electron could spit out a weak particle or absorb a weak particle and become a muon or a tau. You can become different things. There are some rules that have to be followed, but and this is why Feynman diagrams are really useful, because they're basically they're the Pac-Man model of where, who started, what did they spit out, or what did they eat, and what did they turn into. So yes, bosons can interact with each other, kind of. Bosons interacting is weird, but that gets into what Bose-Einstein statistics are. So I'm just gonna... Oh yeah, and they have different spins. All fermions are half integer spin, and then all bosons are full integer spin. So this intrinsic property spin, which happens to have the same units as angular momentum. And it's also something else I'll point out is that depending on how you mix particles together, you can get I could mix if I got 3 quarks and I make up a proton, that proton plus an electron could behave like a boson then. 2 fermions together could behave like a boson as a unit, but they are not a boson. They just obey Bose-Einstein statistics. Okay. So this table's pretty good. There's 4 gauge bosons and scalar bosons. Hey, this is what I was talking about the other week, or I was shouting at someone the other week, where the Higgs boson is the scalar solution to a field solution, where the other ones are gauged. Why make one half integer spin? We could make it integer spin, and the other one 2 times integer spin. I think it has to do with, it's not that they have half, it's because the half integer, I don't want a page on half integer, stupid. I want the page on spin. So it is half because of the unit. We could call it 1 and 2, but all intrinsic spin is in reference to the reduced Planck constant h bar. So it has half of an h bar worth of spin. And there are there are kind of jokes in physics about using natural units. So you might have seen people talk about the speed of light c being 1. Planck's constant scaled to 1 is another form of natural unit. So it is 1/2 of an H bar. And so I could call it one of a unit 2 H bar. That would work too. Or 1 of a half H bar unit. So it just has been easier to just call it half of an H bar because H bars are everywhere. So fermions have to have either have half integer, they either have half H bars or 3 half H bars. And the big thing about fermions is that they obey the the Pauli exclusion principle. So if you've taken a chemistry class and you've done like atomic orbitals and you have to have, if an orbital's full, then your electrons have to go to the next orbital. And if you have an up spin in an orbital, you could fit a down spin by Pauli exclusion, but you can't have 2 up spins. And so that's just a big complicated way of saying, if I have a fermion, what it means to be a fermion is that it is the only particle that can be, it is the only particle, there can only be one particle described by a set of conditions. So if I have a particle in a location, if I got a particle in a location and it has a momentum and it has a spin, there can only be one particle that looks like that. If I have another particle in the same location, then it better have a different momentum or a different spin. If I got 2 particles that have the same spin and the same momentum, that's great, but they have to be in different places. So there's this idea of uniqueness. Fermions are unique, where I can never have 2 fermions that are identical in every single way. There has to be something different about 2 fermions that make them distinct. You could think about Pauli exclusion principle as the idea that matter occupies space. It gets a little, I kind of think about it that way. You do have to keep in mind that there are properties. There are properties that are not spatial properties that can be considered as well. So I can have 2 electrons in the same location with the same momentum, but they have different direction spin. And that is sufficient enough for them to be considered occupying different spaces. And there is no exclusionary principle for bosons. So that is exactly what makes bosons different. So the statistics they obey, the idea of statistics with fermions, do they have anything else here? No, they don't. The idea of statistics of fermions is that as I have if I have an ensemble of fermions and they are taking up space and they have energy, they are going to start becoming more energetic than the last one because they have to be. I can't have 2 be completely identical in every way. So if I have my lowest energy level filled, space is taken up, no room. The next guy has got to go on the next energy level or have a different spin or have some other property. Bosons, on the other hand, bosons are, I don't want to talk about hadrons, that's BS. Bosons are beautiful, and I love them. What's your question? Okay. The point that force can be unlimited and scaled, but matter can occupy space. Kind of, yeah. You could think about it that way. The big thing with bosons is that they are allowed to, they are indistinguishable. So kind of like how, kind of the opposite of what I said about fermions having a uniqueness about them. I can distinguish between 2 fermions. They might seemingly be identical if I swap them, but they have to have properties about them that are different. So they can be indistinguishable, but they're unique. Bosons are not unique. I could have all the bosons. I could have all of the bosons or a pile of bosons sitting together in the same space, with the same energy, with the same spin, with the same everything. They can have identical properties as their buddy. So I always think of bosons as like this big pile of friends, like having a group hug and you can't tell who's who anymore. Space doesn't have discrete units, right? Depends. It depends on how small you get. So yeah. Bose particles are... Oh, that's another cool thing. Fermions are antisymmetric particles, and bosons are symmetric particles. So, like the wave functions for these particles for all bosons is going to be some sort of symmetric function, where for fermions they're going to be antisymmetric functions, which is cool. Bosons. Electron and electron with an identical profile located Yes, there could be an electron and another electron occupying approximately the same position, but not quite. But yeah, that could happen. That is unlikely. So again, like we're in the realm of statistics where I can't like look exactly at the electron, but I have an idea of where it will be. Like the wave functions could overlap. The wave functions can overlap if there is a difference somewhere. So like I can have two particles in the same space, like their wave functions, their probability densities are identical, except that they're different spin, or except that they're different momentum. So this idea of getting them closer and closer and closer together, or having, like, what does it mean to occupy the same space? Because they're, like, these particles have, they have mass, or they have rest mass, they have inherent energy to them, but they don't, like, how big is an electron? I don't know. Like, I doubt that even, dude, let's see. I'm actually very curious about this. We'll talk about Planck constant in a minute. Leptons, blah, blah. Let's talk about electron. So there is not like a size. You'll notice that here they don't talk about the size of an electron because we got mass, we got electric charge, we got magnetic moment. But like the idea of a size is kind of weird because they can be like point particles and they can be like an electron cloud. But yes, so this idea of going back to that like Greek idea of like, if I cut it like in half, when can I stop cutting it in half? When could I stop putting is space quantized is basically what you're asking. If I have two real numbers, I can always find another real number between them. If I have two electrons, could I fit another electron between them and another one and another one? And the answer is, so did I talk about Planck length here? Is this is the Planck constant. Okay. So in, there is a thing called the Planck length. So the Planck length is the theoretical quantized distance of space. The Planck length is the Planck length is the smallest that could theoretically exist maybe there's something smaller than a Planck length, but like how small a Planck length is so absolutely tiny that like yeah, it's kind of conjectural. So the way that the Planck length was derived is, I mean, we can talk about Compton wavelength. So Compton wavelength is it's the wavelength of your particle. People talk about themselves having like a de Broglie wavelength or something. You have a wavelength based on how much energy you have an associated wavelength. And so with the Planck wavelength is where it is the Planck mass. The Planck length is the wavelength of a particle with a mass, Planck mass. And the Planck mass is this is super weird and super cool. So I was talking about units, right? Planck mass is defined as h bar times c divided by g rooted. It is something that it's 22 micrograms. It's like a flea egg. What the Planck length is, though, or what the Planck mass is it is a mass constructed out of just fundamental things. So you'll have physicists talk about natural units, which is actually kind of important. We're going to talk about them. So the idea of Planck units, Planck length, Planck time, Planck mass is basically there are three fundamental constants in the universe. There's the gravitational constant, big G, which like is just a thing. I don't know why it is the value it is. We don't know why big G is equal to however many. I don't even remember what the units of big G are. Like c, speed of light. I can say, oh yeah, in meters per second, the speed of light is 3 times 10 to the 8 meters per second. I can say these things. I can talk about these are just fundamental facts about the universe. There is some gravitational constant. There is some sort of speed limit. And there is the Planck constant. It just is. They are well-measured quantities, but they are just numbers fundamental to the universe we live in. And so what Planck did is he took these three things and he said, well, if I take h bar, times it by c, and divide it by g, these three fundamental numbers about the universe, and I take the square root, that should have the same units as mass. And so I'm going to call this my natural unit, like the special mass. This is kind of what I was talking about with when you set c equal to 1, and you set g equal to 1. And so I can derive units. I can derive a Planck mass, a Planck length, a Planck time. And so, Compton, why would I even talk about Compton wavelength? That's BS. So given these three fundamental numbers, how can I combine them to get a length? That's the Planck length. And it's the tiniest. Planck length, I've got like 3 Planck length tabs open. So a Planck length is defined by constants. Speed of light in the vacuum, Planck constant, gravitational constant. So the dimensions on Planck length are length. It has dimensions of length. Yep, c is a velocity per time. Gravitational constant is a mass, is distance cubed divided by mass divided by time squared. And then h bar. What is h bar? H bar, oh, it has units of spin. The Planck constant has units of angular momentum. So it has units of energy times time, because it's angular momentum units. So taking angular momentum, gravitational constant, which I guess has units of force times force divided by mass times. That's a weird one. This is the weirdest constant to me. So the Planck constant is a angular momentum. So all of those. So the Planck, and that was Planck constant. So if I combined like this fundamental meter distance per time and fundamental constant, like these are constants, they're not derived units. But from them I can Frankenstein them together to get a length. I can Frankenstein them together to get a mass. And so that's the Planck length. Yeah. And it's weird. So the Planck length, in terms of units that I understand, because I live on the scale of meters, a Planck length is 10 to the negative 35 meters. Which is, the Planck length is 10 times negative 20 the diameter of a proton. So, yeah. There's a thing. Zoom in. Scale of universe. This is what I want. This is one of my favoriteest things ever. I hope it still works, because like Flash doesn't exist anymore. Oh no. No. Interactive scale of the universe. If you're gonna link me, shut up. I'm very upset right now. Scale of universe. Scale of universe. This is the exact same length, and it's not going to work. Why is it not working? I'm very upset. I'm very upset. Scale of universe 2. This looks sketchy, but we're going to do it. English. All right. So, I love this tool. I think it's super great. This is going to show us how absolutely tiny a Planck length is, where hypothetically I couldn't fit 2 Planck lengths are as close as any 2 things can get together. So here we are. This is a meter. It's great. Yeah, this is a person. It's about 2 meters. Dodo bird. So we can go out and look at like, oh, this is T-Rex. You say that the exponent already tells us, but like that means nothing to me. The exponent, like, it's there, but I don't understand. But I understand this. Let's go in. Going in. We're getting tinier. We're getting tinier. Oh my god. So like this is the edge of visible light on the 10 to the negative 6 scale. And like this is viruses. And we just keep going. So we get to atoms. Then we get to the classical size of the electron, And we keep going. Neutrons, protons. Okay, here's the big thing. Lengths shorter than this are not confirmed. This is a small, 10 to the negative 16 is as small as we've been able to like measure physically. Hypothetically, the weak force works on range of 10 to the negative 17. So I don't know. I feel like I talked about like the history of the universe with the Big Bang. So the idea of particle accelerators is to try and create conditions where the forces were united and things were hot and things were really close together. And so that's what this is. Well, we get to know about the weak force at this range, which corresponds to an energy that can only be achieved in particle accelerators. And so this is how big quarks are, maybe, because we haven't confirmed lengths smaller than this. Hey, neutrinos. I used to do a lot of research with neutrinos. And we keep going. And we keep going. And we keep going. Hi, neutrino. I love you. And we keep going. And like each one of these is a power of 10. And like this is, it is smaller to go in. Sorry. What am I saying? The size of how tiny, yeah, here, Planck length. Here we are. So string theory, I don't know a whole lot about string theory. I am never going to claim to be someone who can do string theory or quantum gravity or any of that stuff, but those theories are built on the idea of working up the Planck scale. So string theory, if I'm remembering correctly, is what if the universe is made up of a bunch of like tiny little wavelengthy things that are Planck length? Like, let's zoom in as far as we theoretically can zoom in, knowing what we know about universal constants. So the reason that they would be put, just for if anyone watches the VOD, is there any reason for quantum foam or strings to be at Planck length and not smaller? So the barrier keeping us from going smaller is that, like, I guess you could, but for example, I could go faster than the speed of light, right? Like, theoretically, there's nothing keeping me from investigating solutions or speeds that are faster than light. They're not physical, and my models will break down. And so the same thing happens with Planck length. You can think about it much like the speed of light, but it is the universal distance thing. There is a mass constraint about going faster than the speed of light because of how like inertial and relativistic mass work. I don't know enough about Planck length. Let's see if there's more. Theoretical significance. So Planck length is the scale. So you could potentially go smaller, maybe. But it is at that scale that they think quantum gravity would come about, because the Planck length itself is made out of the speed of light, spin with Planck constant, and gravitational constant. So it is a combination of the universal constant that has to do with relativity, the universal constant that has to do with like spin and quantum, and the universal constant that has to do with gravitational effects. So it's kind of like the marriage of the three. Planck area is the area. What? Sorry, this is new to me too. And this is very cute. A Planck area is the area by which the surface of a spherical black hole increases when it swallows one bit of information. That's dubious. Discuss. So, like, lengths... Oh, okay, so the main role in quantum gravity is played by the uncertainty principle, where the gravitational radius and the radial coordinate and the Planck length. Okay, so there's an uncertainty principle of where the Planck length squared is kind of your uncertainty in lengths at that scale. So yeah, I guess you might be able to have something smaller, but it is the order of magnitude where things start getting weird. Just like, or it is the scale at which you would have to have quantum gravity effects. Just like I don't think about, like, when I touch my hands together, I'm thinking about this as a contact force. But if I zoom in really, really, really close, I can see that it's actually, like, the electrons in my fingers are repelling each other, and it's actually an electric force and not a contact force, right? So this grain size, this scale that we're looking at, is very relevant to how things behave. I want to do cosmology again. Physical cosmology, that's what I want. Physical cosmology. You have this. So this idea again that as the universe expands and things get older, that is not the image I want. Timeline of the Big Bang. That's what I want. Timeline of the Big Bang. God, this is... Oh, here it is. Yeah, so the Planck epoch is when the universe was the size of a Planck length. And it happened this time ago and was this hot. So if I can match this energy condition, I can, like, recreate that time in the Big Bang. Whereas galaxies form here at about 60 Kelvin. Well, that's like now. So I can, if I have anything this hot, it tells me about the physics from this time in the universe. If I have anything this hot, it tells me about this time in the universe, 1 second after the Big Bang. So if I can get something that is 1 mega electron volt, I can see that is where I start seeing neutrino decoupling effects and stuff. And so the Planck epoch is 1 on the scale of a Planck time, where a Planck time is the time that I can derive from the universal constants. If I combine the universal constants in a way to get units of seconds, that's a Planck time, and it's got to be really energetic. Yes. Yes. So does the Big Bang predict a natural starting point for the calendar? Yeah. There are actually a lot of really fun ways to think about the universe in terms of, like, a calendar year, where, like, if right now is midnight, like 12:59 and 59 seconds and 99 hundredths of a second right before midnight. And yeah, so the Big Bang happens on 0. Then the forces start diverging from each other at that many seconds. Um, and yeah, those are really fun. If the entire like life of the universe was a calendar year, humanity has only been around for like 2 minutes maybe of the entire year. Um and the earth has only been around for like a couple months. Cuz the earth's what, 4 billion years old and the universe is like 14. So yeah, earth's been around for like 3 months. That's a very fun exercise. It was something that we used to do, or when I used to teach the astronomy class at my university, one of the activities we would do is, you got a year, here's an event, calculate, if the Big Bang happened at 0, calculate when this event like would be on our calendar year. I think that they did that in the Cosmos TV series too. But we're like, I think we're at like 12. We're like right here. Sorry, when I say we are like right here, what I mean is, this era is where particle accelerators are able to like zoom into. This is how much energy we're able to get. We're not yeah, we're right about here, I think. Because we're not at grand unification yet. Yeah, 4 out of 14 is not bad. Earth's doing pretty good. She's a little bit. And the sun, I don't remember when the sun formed. I think the sun's older than the Earth, but not by like a ton. So like I initially was very interested in particle physics because of the connection to cosmology. I don't actually really like the particles. I mean, I do. They're cute. But they're a means to an end. Like, discovering cool things about particles is cool because it is looking back in time. It is looking at what happened shortly after the Big Bang and is giving us clues into the formation of our universe. One of my favorite epics is the Dark Ages. So this is where the cosmic microwave background comes from. So what happened was the universe was like as it expanded, it got super, super hot, and there were all of these electrons and photons coming about, and they were emitting and they were absorbing and emitting photons between each other so fast that like there wasn't even like really light yet because they were just so hot and so dense. And then after that, when they spread out enough, yeah, right here, this is where it says it. The universe first becomes transparent. So this is where the light and matter, it has spread out enough that like light can pass from one atom to another atom without hitting another atom. Like there's space between things at this point. And so the universe becomes transparent. And by becoming transparent, it also means that it can emit light that doesn't get immediately reabsorbed. And so as these photons are allowed to be emitted and not be absorbed by anything and just kind of like float free and go out into the universe, that's where we get the cosmic microwave background. Is that they were, yeah. So before stars were made, but after this like super hot dense plasma happened, there was like nothing. There was just like space gas everywhere. Just hot space gas floating. And then it wasn't until millions of years later that the gravitational forces of the gas started to pull it together, and over millions and millions of years, the atoms were like, hey, instead of being hot and feisty and bouncing around away from each other, my gravitational attraction to you is coalescing me into a little star. But yeah, cosmic microwave background's cool. Did you know? I feel like this is true. I don't think I'm talking on my ass. But the cosmic microwave background is what caused TV static. Like if you have an old analog TV and it's just like, that is the TV, like the radio TV antenna picking up just the ambient background, which is the cosmic microwave background radiation. Dude, this stuff is so cool. I love thinking about this too, because it's like the universe in the past is giving me a giant hug. Like just this radiation's all around me. The universe became transparent instead of being an opaque fog. Super cool. This is also where the temperature of the universe comes from, is the cosmic microwave background, because so any sort of light source or radiation source has an associated temperature. If you treat it like a black body, you may have heard of black body radiation. This is how we like estimate how hot stars are, is we look at their emission spectrum and then we can calculate their black body. Using their spectra, we can calculate the thermal black body spectrum. And so the universe, sometimes it's called the 3-degree background. So the ambient temperature of the universe is not 0 degrees Kelvin. It is 3 degrees Kelvin because of the cosmic microwave background. There is enough just ambient light and radiation out there that it's not absolute zero, which is kind of cool. I love the CMB. It's so cute. It was a pretty big deal when it was discovered. When was it discovered? Yeah, it was a complete accident. It was a complete accident. It was discovered in the work that started in the 40s, in the 60s. So this is actually relatively new. Like if we think about the scale of physics discoveries, CMB is like super heckin' new. Wow, so we started talking about cosmic microwave background because you asked about fermions and bosons, and I don't feel like I really answered questions about fermions and bosons. I got so distracted. I'm sorry. Did you have any more questions? Should probably, be on task. Assuming the universe is infinite, Big Bang predicts a void outside of the range of the Big Bang and the scattering of particles. So, if we do the opposite, if we go out, so the idea of the edge of the universe, so like we keep getting bigger and bigger and bigger, like this is how far light travels in a year, we get bigger and bigger and bigger, we zoom out. Yes, there is stuff outside of the observable universe, maybe. Clusters. Huge. Okay, so this does a pretty good example of that. The observable universe is 10 times... I also love that they made it static, because that is... everything past that would conceivably just be background. I don't know where the center of the universe is. We don't know where the center of the universe is. Everything is accelerating away from each other. The universe is expanding. But like it would be very, very human of me to assume that we are at the center of the universe. But we are at the center of what we call the observable universe. So the farthest light that I can see out, the farthest away I can see in any direction is 10 10 to the 27 meters. Or the age of the universe, like 14 billion years worth of light travel. So 14 billion light years is like 10 to the 27. Yeah, presumably, like, we can't observe most of the stuff from the Big Bang. Or if they're, like, was there stuff that got pushed out faster than the speed of light right at the beginning of the Big Bang? I don't know. If there was, then that is beyond our reach, and we will never be able to see it. And it is perpetually getting harder and harder to see it because it's getting farther and farther away because the universe is continually expanding. But yeah, like, I mean, we might. Who knows? We might, like, if the universe, let's just imagine that the universe itself is a perfectly expanding sphere. What if, like, the Earth got formed, let's say this isn't the observable universe, but this is the actual universe. And instead of being in the center, like, what if the Earth's right here? And we only see this zone here. We only see 13 billion light years around this point. But, like, if there's a planet at the edge of our visible universe, conceivably they then have 13 billion light years that they can see around them. And so how far does that keep going? I don't know. This is some like eldritch horror, man. The universe is too big. It's too spooky. But, you know, I freak out about, like, having papers degrade or something, or not being on time to a meeting. That's small stuff. Don't sweat that stuff. The universe is literally too big and you are too insignificant to matter. And I don't mean that in a negative way. I mean it in nothing matters. It's great. The universe is so big. I'm just, like, I'm smaller than an ant. It's great. But yeah, there's probably stuff out there. I would say that there's more likely to be stuff out there than not. Oh, has this been making sound the whole time? I hope the music wasn't just absolutely awful. Oh, okay. I should probably go eat dinner and go tend to my cat who was spicy. I don't know if she was spicy that she didn't get enough screen time or that she got too much screen time, but I don't know. Anyway, I'm gonna head out, but thanks for hanging out. I'm glad we got to talk, and I'm glad that I'm not going to use sugar to get to the moon. Anyway, thanks for hanging out.